All right, let us look at this problem called longest path with different adjacent characters. So in this problem, what's given to us is we are given a tree representation, and the way the tree representation is given us to us is using this parents array. So there are n nodes, and for each node, there is a parent array given which tells what is my parent, and parent of 0 is set as -1. That is how the tree is given. And another information that is given to us is for every node, a character label is given, which is through this string array. So which tells which is the label given to this node. And our job is to find the longest path within the tree which does not in which the adjacent nodes do not have the same character. So for example, if you go from 0 to 2, both have same adjacent, the adjacent nodes have the same character a and a, so it does not work out. So for example, in this case, the longest path is 0 to 1 to 3. 0 to 1 to 3, where okay, a, b, c. Similarly, in this example, the longest path, if you see A and A match, so you can't use 0 and 1, but you could use 0 and 2. So you could do like this BAC or this CAB. So that is the longest path of length 3. So that's what we have to solve for. So let's use a whiteboard to understand how to do. So the key thing to in any sort of problem which requires finding path within a like finding some sort of a path or maximum path for certain conditions in a tree is how you so first of all, what is a path, right? So let's look at 1, 2, 3, 4, 5, 6, 7, 8. I don't know, some random thing, right? And so now, is this a path? Yes, it is a path. Can I say within this tree 1, 2, 4, 5? Can I say this is a path? Obviously not, right? So what is a path? So path has two AND nodes and then multiple nodes in between and through which you can reach to that path. So this if I start from 4 to 2, you can't have multiple AND nodes, right? That's the thing. There are two AND nodes and you traverse among the intermediate nodes to reach to those nodes. So that is something that we need to be wary of. So, for example, yes, 2, 4, 5 can be a path. 9, 4, 2, 5. This can be a path. 8, 6, 3, 7 can be a path, right? But so when you're saying we are saying this 8, 6, 3, 7 can be a path, but this is now not a path because now you're getting multiple AND nodes. There are only two AND nodes in your path. So that's something we have to be wary of. So now let's talk about how you can build up your path information from children to the parents. So let's say this is a node and it has multiple children, right? Child 1, child 2, and child 3. And whatever condition that is required, let's say each child can give a longest path along itself. So let's say it says hey, I can give you this much path. This guy says I can give you this much, and third guy says I can give you this. So like these are the three different with three different children you can give these long different paths. Now so this is L1, this is L2, and this is L3. So now if you have to say longest path centered around this node X, what is the longest path centered around this node X? Well, you can essentially take any of these two legs and join them, right? So which would be it's either L1 plus L2 or L2 plus L3 or L1 plus L3, any of that, right? So essentially, what's the basis? Well, just take the maximum large. If you want the largest, so you will take the two largest paths, right? Out of all the child paths, and plus X the node itself, right? So you'll take this node itself, and in this case, you will take this L2 path plus this node plus this L3 path. So this will be your longest path around centered around this node, right? That's one information. So longest path centered around X is 1 plus L2 plus L3. So that is one of the paths to consider in the overall tree. But now another bit is, let's see now, how does X pass that an inform like a longest path to its parent? So let's say X has a parent as Y. Now, yes, while the longest path centered around X was 1 plus L2 plus L3, that would no longer be a path, a valid path for Y, right? Because then it will get three different endpoints. There were two endpoints this and one endpoint Y. So what Y can use from X is only one of the legs, any one of the legs. So what will X pass to Y? Well, it will pass 1 plus max of L's, right? Any one of them. So it will, in this case, it will pass 1 plus L3. So Y can see, Y if it wants to have one of the legs coming through X will take this as one path, and some other children of Y will give some other legs, right? So say Y will have another child, Y will have another child, and now between these two, so let's say this is L4, this is L5. So for Y, the maximum path would be L4 is the biggest, and after that is 1 plus L3, right? So let's say it will be 1 plus L4 plus whatever X returns, which is 1 plus L3, right? That's sort of an idea. So let's build a logic based on this information. So first, let's build the tree using adjacency list-based representation. So we are given this parents array, right? So let's have a list of teachers, and we have let's say an adjacency list, new array list. Now for each I equals to 0 is less than plus. So from each parent add, let's just add the, yeah, it's an undirected graph, but we really need information from parent to child. So we'll do, okay, so here let's first do adjacency list dot add new array list, right? So a list of list, and then we are going through this parents array. So for equals to 0, I is less than parent of length, I plus plus. We know that parent of 0 is -1, so we don't really care about that, right? So we ignore 0, and what we're going to do is this: in the adjacency list of the parent, we're going to add the child, and let's have those links from parent. All the parent to child links now is what we have, and we have to return the longest path. Let's define, there will be at least be one node in the tree, which is mentioned that number of nodes is at least one. So we define the longest as one, and then eventually we want to return this longest. I also want to maybe update longest within the recursive call. So I'll make this a global thing. So I'll do longest equals to, and you can maybe initialize it again for multiple function calls. So that is fine. And we're gonna return longest. In between, what are we going to do? Well, we can do something like find longest, and what are the stuff that we're going to pass. So we start from root, and we're going to pass in the adjacency list based representation. We're going to pass in this label information, and I think that's it, right? So now let's say int find longest. This is my index, and we have the adjacency list based representation, and we have this character array which gives me label for, let's call it label for each node. And so what are we trying to find here? Okay, so we first want to go through each and every parent, right? And like we know, we have to choose two legs out of the different child we can get. So let's define longest leg equals to 0, and then second longest leg equals to 0 as well. And now we want to go through each and every child, right? So for each neighbor in the adjacency list of index, so for each child, let's just call it child, So what lag we are getting from this child? So this child, the lag that we are getting is just to find longest. So child index is child adjacency list and label. So we're the longest leg from the child. Now we come to the condition, and the condition is there should not be adjacent. The adjacent node should not have the same label. So only then we consider it. So if my label, so if label of index is not equals to label of this child, then I'll consider this as a valid lag. Otherwise, I won't even consider it, right? So now, at least for this node. So now what I'm going to do here is, if that's the case, then I'll do if this child lag is greater than the longest lag, then I'll update the longest lag, right? So the longest lag will be child lag. But also, we are maintaining second longest lag. So if you're updating the longest lag, that means your longest lag is increasing. That means your second longest lag becomes what was actually your longest lag before, right? So second longest lag equals to longest lag. That's the case. And already, if the child lag is not greater than the longest lag, then we might also want to update the second longest lag. It could be actually greater than the second longest lag, right? So if that's the case, then we do, and we get this two longest lags from all the child. Now, uh, now let's consider the path centered around this node. So which is what the longest that we are maintaining, right? So this longest equals to math.max longest, and what is the maximum path that I can get centered with this node? Well, this node itself plus the longest leg that I can get, plus the second longest leg that I can get, right? And that's it. And what will it return to its parent? Well, it will return to the parent the longest lag that a parent can use, which will be what? Which will be one plus the longest lag only, not the two nodes, because that the number of ends increases, but only one lag, right? So that's what we discussed in the beginning. So it will return to the parent one plus longest lag, which its parent can use. So overall, we find the maximum path centered around each and every node and keep track of the longest this way. So let's run and fix any compilation errors. And we do get a compilation error. Let's see. It's not a statement. We missed an else. Sorry, we missed an if. Let's run again. And the two test cases gets accepted. Let's submit and see if everything gets accepted or not. And everything gets accepted as well. So, I mean, there are multiple questions like this where you have to find the max path some within a tree and similarly, but general idea is what you consider the path centered around each node, and the way to get that is the longest, basically the longest paths that each of your child can return as a leg, and what you return to your parent is again the same thing, which is the longest leg that your parent can use passing through yourself. And obviously, so there are two separate things, considering the longest path centered around yourself and the longest leg that my parent can use. And if we understand that, then it's easy to solve problems like these. All right.